Okay, now let me take a small example and see how whatever we have covered till now regarding the representations, how that can be handled with the use of this small example. So suppose we have three documents, D1, D2, and D3. D1 says it is going to rain today. D2 says today I'm not going outside. And D3 said I'm going to watch the season premiere. So at the very beginning, we need to process the inputs before we get the representation. Now, one important part of that processing is to extract the individual words which are appearing in those documents. So it's very easy to see that the first document has the words as it is going to rain today. So these 6 different words are there. And second document similarly has some words and so on. Now, given a sentence, splitting it at appropriate places to get the words is the very basic first step. And there are many different simple functions which can actually take as argument an input text and a set and a list of delimiters. So whenever those delimiters are found, it says that, okay, my current word has ended there and I start a new word. So like that, there are many different splitters which were there. And it was not very difficult to extract the different words from the text. Typically, this part is called tokenization. So whatever is the output of this splitting is called a token. So every single thing that we get out of this, every single, let's use the term word here, that we get here is a token. So it is token number 1, is token number 2, going is token number 3, and so on for the first document. Okay. So this step is called tokenization. And so first document will result in 6 tokens. Second documents will result in 1, 2, 3, 4, 5, 6 tokens again. And third document contains 1, 2, 3, 4, 5, 6, 7, 8. 8 tokens. Now, once people, so they always started with a collection of documents. And if D2, D3, D2, D3, these 3 things are part of the collection. After they process these tokens, the very first step was to then output a vocabulary. Vocabulary is something like a dictionary that we have in any language. However, in a language specific dictionary, we'll list down all the different words which are possible in that language. And so it requires a knowledge of the language, right? So people who are aware of the language well, so they together prepared that dictionary. However, here we are not looking at all possible words, right? So when we restrict our document collection, in some sense, we are also restricting the words which are appearing, the words which are considering. So that way, vocabulary construction is based on the input collection. So here, this vocabulary will contain all the distinct words which are present in this collection. So although the total number of tokens here will be 8 plus 6 plus 6, which is 20, the number of elements in the vocabulary will be less than that because there could be some terms which are present in more than one document, right? So in other words, if S1 is the set of words in D1, S2 is the set of words in D2, and S3 is the set of words in D3, the vocabulary will be, can you write the vocabulary in terms of S1, S2, S3? Anyone?
It's S1 union S2 union S3.
Correct.
Cardinality of this.
S1, S3. So the vocabulary is a set which is the union of this. So in other words, if we have I different documents, so this one will be union over all SIs. And, and the number of words in this vocabulary will be the cardinality of this. The vocabulary is a set. So it's once you keep processing the documents, you can also assume that suppose you have a very large collection, you are reading one document, you are tokenizing it, that is, you are splitting it into tokens, and then you can create this vocabulary in an incremental manner. And uh, in an engineering way, it may be time consuming and so on, but the steps are pretty simple. Every time you get a new word, you essentially check whether it's there present in the vocabulary. If it is present, you don't have to add a new uh, word there. If it is not present, you add. So like that, your vocabulary will keep expanding. Now, there are many other things, statistical properties of this vocabulary that uh, people came up with. Like sometimes it. So, what is the distribution of words in the vocabulary? So, although so sometimes in the vocabulary may be more prominent in the collection, sometimes maybe less prominent, and there is Zipf's law, which actually gives the distribution. I mean, which can be used to estimate the distribution of the different words in the vocabulary. Then people also say that, okay, suppose I'm designing my system and we'll look at the different representation techniques. It may be important for me to reduce my vocabulary size. Right? If you look at all the number of different words which are there in the English dictionary, that can be, I don't know how much, 50,000, 60,000, 1 lakh. So it may be difficult for me to work with that larger vocabulary. One may say that my device is small, I do not have a lot of compute power, so I need to restrict my vocabulary small. So what could be the different ways in which I restrict my vocabulary? So all these are different considerations with vocabularies, and everything, even today when we talk about language processing, this vocabulary becomes a very important thing. So based on the collection, how do we learn good vocabulary which is suitable for my task? All right. So coming back to our this example, given the documents, uh, following some basic rudimentary steps, we can construct this vocabulary. Now, what the very first representation said that, okay, if I assign some ID to all these words, then I can, so suppose it has ID1, is has ID2, going has ID3, then 4, then 5, 6. Then the first document can be represented as D1 in set representation. It can be 1, 2, 3, 4, 5, 6. Then there was one more. Then people said, we can process sets and so on, but we know that. But if you look at two different documents and see, whether they're similar or not. So with set-based things, sometimes it may become slightly difficult or difficult to process, or slightly difficult to visualize. On the other hand, if you go to vectors, right? So vectors are a very nice property that they can be viewed algebraically and also geometrically. So due to this geometric angle of the things, people say that, okay, we can then now look at the vectors, and we know that the vector operations are typically cheaper, right? So two vectors, we can add them, and that has a special meaning. We can do subtraction, we can do multiplication, and so many other things. And since the elements of vector, they stay close by, when we process them in our say processor, we can use many different aspects of computer architecture like temporal, spatial co-location and so on, so that elements, if they are close by, processing also becomes faster and so on. We also saw many times, so people had many different optimized linear algebra libraries and so on. So if documents somehow we are able to represent as vectors, we can make use of all those interesting properties to get the computations in a faster way. So they said, okay, then why not represent them as vectors? Now, if you think of vectors, there are two things in a vector. One is the dimensions, right? So how many dimensions does the vector have? And secondly, what is stored in that dimension? So if we have this thing, our vector is this. So if we say that each document we want to represent as a vector, so we need to see how many dimensions it has and what will store in each of these dimensions. And if we view geometrically, then say, okay, a vector means, there will be different axes. So we need to see how many different axes are there. And then know how much one should go in each axis to uh, store a specific document. So this was important. So very first thing, obvious choice that people say that, okay, each of these terms that we have, I think here we have how many? So 14, 7, 8, 9, 10, 11, 12, 13, 14. 14 terms in the vocabulary. So each document we will represent as a 14-dimensional vector. So this is what we can do. So each document D1, D2, D3 will be represented as a 14-dimensional vector, and each dimension will correspond to one term from the vocabulary. So it is the first dimension, is the second dimension, going is the third dimension, and so on. And so that takes care of the number of dimensions thing. But what to store? We can say that we can store the presence of or absence information. So D1 has the first 6 words. So for the first 6 positions, D1 has 1, and the remaining, so it's a truncated table. Once it will have zeros. Then D2 has the words today I am not going outside. So going is there, today is there, I am not, these words are there, but to rain, these things are not there. Now again, a very simple kind of representation technique. So it's a Boolean representation. Okay? So it's a Boolean representation. So that means for each term in the vector, we store either a 0 or a 1, and our understanding is that 0 means absence of the term, 1 means presence of the term. Then people say that, we mentioned this point earlier, that the frequency of the words may also be important. That is, if a specific term is occurring more and more, we should give more importance to the term. And in vector terminology, giving more importance to a dimension is something like you increase the weightage of the dimension, or whenever you encode, you store a large number here. Whenever you store a large number here. So then people said we can use the raw frequency of the term, or how many times the term occurs in that document. So it's called the raw frequency. However, this raw frequency, usage of the raw frequency of the term, results in many unwanted situations that there is an explosion of the numbers. So typically, if you have a large collection, the vocabulary size that you extract like this may actually be large. And in that very large space, if there are some cells which have very large numbers, essentially there can be some explosion of numbers, because later on you will do some operations on top of that, right? Large numbers, they getting added together. So at some point of time, it may be very difficult to handle. And at the same time, it also results in noisy capture of relative importance. So what does it mean? That suppose there is a term which occurs 2 times in a document, and in another document it occurs 20 times, or say 10 times. Now, if we use the raw term frequency, then in some case, for the first document, we are storing 2 here. For the second one, we are storing 20 here. So which somehow gives an indication that the importance of this term is 10 times more in this document as compared to this document. Now, this is something that people say should not be the case, because whenever we keep adding a term more and more times, the marginal utility that the term has in that document does not, it diminishes actually. So it's not that this document D3 is now 10 times, or this term is 10 times more important in D3 than D2. So in some sense, it captures the relative importance, this relative importance in a noisy way. So people said instead of using the raw frequency, we'll use some function of the frequency, okay, which has some properties but will not use these terms, these numbers directly. So what are some of those properties? So one property is that if the occurrence is more here, the weightage should be more here. Okay? So we'll try to have instead of storing the count directly, we'll use a function of this count. Let me write it as g. And what are the properties of this g? Is that it should be an increasing function. It should be an increasing function. So what do you understand by an increasing function?
If x1 is greater than x2, the f of x1 should be greater than f.
Exactly. So precisely that is the definition of uh, an increasing function. If the argument of this function increases, the value also should increase. In other words, as it was told, if x1 is greater than x2, then gx1 greater than gx2. So can you suggest some simple functions which have this property?
Square function.
Square function.
Like exponential polynomial function or linear function.
Not really. All
Means from the domain of 0 to onwards, like in polynomial case.
I think log could be a monotonically increasing function, right?
Yes. So one very simple thing could be like fx equal to x plus 1. That's a very simple function. It's also a polynomial in some sense. So whenever we say polynomial, we need to restrict the range because if it becomes negative, for example, instead of x square, suppose we put minus x square,
Yes,
or
yes.
then it does not have. But yeah, so I believe you all understand. Then log is one another choice. So this was the thing. People said, okay, we'll not store the raw count, we'll use some function. But then there are so many different functions to experiment with, to choose from. What could be some of those functions? There also, it somehow became a game of, not a game of, an exercise of trying out different functions and seeing if I use it in my representation scheme, is it helping in my further processing tasks? Okay? And it's not always the case that, okay, every possible function we need to enumerate and then we need to pick. People also try to see if the function has any other desirable property. So here also, I mean, based on the whatever discussion we have, so we said instead of C, we'll store G of C. Now suppose this is one choice, x equal to x plus 1. Sorry, fx equal to x plus 1. Do you think it's a good choice? Okay, I do not think it's a
No.
good choice because all these 2 points, right? It will be there with x plus 1 also. Then
Yes.
Yes, yes.
now suppose we have something like x square or something. Absolutely no use because these problems will remain there.
Yeah.
Now, can we use something like square root of x?
Yes.
Provided that, okay, yeah, but count would always be perfect.
Yeah, we'll deal with positive numbers only here. I mean, that was the assumption. Raw counts are always positive. So yeah.
If x are more than square, then the problem will also arise slowly.
Right. Point is well taken. Then the other function is log. So if you have to choose between square root of x and log, which one will you choose? And can you give some justifications for that?
So can you repeat the question?
We said that instead of raw frequency, we'll use a function of the raw frequency. Now, suppose I have one choice, which is fx equal to square root of x. And when we say square root, we take the positive square root. Another is gx, which is just log. So which function we use, or which function is a better choice for determining what weight to store it, fx or gx?
The gx is better because it is asymptotically lower than fx.
Okay, anyone else?
If log also makes bit of calculation here rather than
Okay, anyone else?
The slope for log x is better because the slope for log x will be lesser as the x increases compared to fx.
So I think all these answers that you have got so far are valid answers, and this is why log x is typically chosen. I mean, this log function is typically chosen. One thing is that the rate at which fx grows, it's still much higher than rate at which gx grows. So if you plot the function of square root of x, and if you plot the function of log x, you'll see that after some time log is actually, the gap between them is actually quite high. Log is still quite high. On the other hand, square root of x is actually quite higher value it has. On the other hand, for log x, the value tapers very soon. So the rate of growth is much lesser in case of log x, or the damping is much more in case of log x. So if you think of, say, legal document case, there will be terms we are talking many times. And both these are increasing functions, which are fine. But after sometimes, adding of the term one more time, it should not contribute a lot. So that way, as we go along, the overall damping that we expect is expected to be more. So it's something like growing and then kind of saturating. So this kind of nature we would prefer. And this is why log-based functions we will have chosen for this kind of scenario. Now,
can you please explain the damping to me?
so if you plot square root of x, and I don't know whether the curve will be of this. No, it should not be like this. Maybe something like this. And log will,
it will be convex.
so if you look at the function for log, that function will start increasing, but the rate of growth will slow down, and then it will kind of flatten, but the rate of growth will become very slow. On the other hand, square root of x, for 1 it is 1, for 2, 3, 4 it is 2, for 9 it is 3. It will stay higher, and this gap will be significant as x grows. Okay, now since we're talking about this math part, a fun thing to try. Can you show that the square root of x will have higher growth than log x?
So if you take the differential,
We will divide them and we'll check the ratio as n tends to infinity.
And then how will you make the judgment that this one grows faster? You said check, but what exactly will be the check?
So So for example, if under root is in numerator, yeah, so it will tend to be infinite as n tends to be infinite.
The other thing that we can do is, say, suppose we have a square root of x and then log x. So this difference we look at. So suppose this difference is y. Now, as x changes, this difference will also change. What will be the nature of change that we can find by computing dy dx? And here in this case, square root of x, this will give you 1 by 2 root x as the derivative, and this will give 1 by x. Now you can do some simplification, as 1 by 2 root x can be there here. This 1 minus 1 by root x. After some point of time, x is larger than 2, or larger than 4. This will be larger than 2. This will be a proper fraction, 1 minus some proper fraction that is more than 1. And x is positive, is greater than 4. So this is also positive. So this part is greater than 0. That means dy dx is greater than 0. That means rate of change here is greater than rate of change here. I mean, again, simple mathematical algebra I can find. Okay, so coming back to our
Sir, one question on this. For the same reason, won't it be better if we even use iterated logarithm instead of simple logarithm?
people have used that also, and they have found that one more log before that log has actually been beneficial for at least the web search kind of scenarios. So log kind of.
Yeah. Okay, thank you.
Okay, so then people said log, and they said log can actually have any base, right? So they fixed that. Okay, we'll be using base 10. Well, that was a choice, and other things can also be done. But as you know that log b to the base a is equal to log b by log a, right? Now, instead of 10, if you want to use any a, you can actually very easily see that the result will be nothing but a scalar multiplied by this log 10 value. Right? So log b to the base a equal to this one, log b by log a. Now, suppose instead of log 10, we want to use something else. So log 10 will be log 10 to the base b equals log, and here we're talking about natural logarithm for this right hand side, log b by log 10. This log b by log a is nothing but log b by log 10 into log 10 by log a. Log 10 by this 10, not b, log a. Now, when we are talking about fixing some a, so log 10 by log a now becomes a constant. Right? So, no. Yeah. A is fixed, so log a is a constant. Log 10 is definitely a constant. So this is nothing but a new constant k. So log b to the base a is equal to a constant in log b to the base 10. So it's a simple scalar multiplication. So somehow there's a strength of representation remains similar. So they said, okay, let us fix that. And So the final value that we want to use, that function becomes this one. TF stands for term frequency, but it's not the raw frequency. It is some function of the raw frequency. It takes two different arguments. One is the term, okay, and the second one is the document. So how many times this term appears in this document? So that part is count TD, count of T in D. And the value that we'll be storing is 1 plus this thing. Again, it's becoming messy. We resolve this here. Yeah. So that's how people reached this function as a good term frequency function. And then through experimentations, they showed that okay, this is actually a good choice, which has the interesting properties or desirable properties. And yeah, empirically also, it provides good results. Now, if this part is clear, my next question to you is that, do we really need the 1 plus thing here, or we can simply have, log 10 CTD?
One being like a normalization that we have everything based. The least can be log count is 0 log so in that scenario it is
So
handling
in that case, if we do not want the lift, then log 10 CTD, even that can be used. Is that what you are trying to say?
No, I'm saying that in that case, basically we are just providing a normalization that any value that we are getting would be uh, 1 plus whatsoever the value. Our threshold would be set to 1. That is a kind of normalization that it is bringing in for the sake of.
Okay, so whatever you saying, that everything will be boosted by 1, right?
Yeah.
It's not normalization, but okay, you are saying that it can be boosted by 1. Okay, any other answer from any?
Sir, I think it's just
Is
working.
it to
Hello.
Uh,
Yeah, because if we look about the probabilistic interpretation, so then if one term is not there, then it will result into 0, so which will make the whole term to be 0. So that's.
So sir, the thing it looks like suppose it's the log term is 0, then suppose we are multiplying something with TF, then the value of that multiplication will be ended up 0, even though it should have some weightage. So to keep it a positive term, we have to use the log 1 plus with the log. I think so.
Can you please repeat that? You are saying we are multiplying and we are 1 plus.
I'm not sure. I'm thinking that if
Yeah,
the
sure.
multiplication term is there, suppose some value we are multiplying with TF, okay, some A into TF. So if the TF is 0, then that A into TF will give a 0 result. Like there is no point of multiplication with the TF. So to keep the TF in a positive term, so we need to have that 1 plus, because log 10 of count of D could be 0. So if we keep 1, so it's like what we do in naive bias, right? We normally do that normalization, that 1 plus something to keep that value as a positive value, the count value.
Okay, I think somebody else also wanted to say something. Any other views?
unless it is used in the denominator, I don't think one is needed.
Okay, so let me give you the reasoning for this. See, this one is needed. Okay, it's not because otherwise the term will result in multiplication by 0 or division by 0. It is because if you look at the value of C, D, comma D, this says how many times T is appearing in D. It can be any number starting from 0. Right? Now suppose the term occurs one time. Okay? Just as any term here. Now In that case, if we simply have log 10 C TD, 1 plus thing we do not have, then it becomes log of 1, which is nothing but 0. And for the purpose of all these processing, log 0 is also defined to be 0. Now, which means if we do not have this extra 1 plus, whenever term is present one time, we will have it 0. That means we'll lose that information that the term is present there. So this is the reason why this 1 plus has been added, and TXTD, this thing is actually written as if C T D greater than 0 and 0 otherwise. So if we do not add 1, when the term is present only once, then also this TX becomes 0 and we are storing a 0 here. So we are not able to distinguish between whether the term is present here one time or it is not present at all. So that's about this function. I think now it's kind of clear why this is a choice. It may not be the best of choices, but what makes this function as a principled choice for this kind of representation. Then, if you remember, is there a question?
Sir, can you please repeat how you are handling if the term frequency is really zero, like if the term is not present in the sentence?
Okay, so if we have a document like this and we want to get its representation, what we do is we extract each token with this document, and this we maintain, say in some structure, it can be a list or whatever. And against each term, we are also maintaining how many times it appears. Once we have that, we can actually go ahead to build this vector. So we see what is the count against this word. If it is 0, we'll directly put a 0 here. Okay? And if it is non-zero, we'll apply this function and store it there. Is it clear?
Oh, yes.
Sir, in this way, some word can have duplicate same value, right? If same word appears in all the document, then that word will have the same number.
Not really. Suppose the word it appears 2 times in document 2, 3 times in document 1, and 3 times in document 3. Then the value here and the value here will be same, and the value here will be less than that value.
Oh, but if in document 2 also it is 3, in that case it will
Then,
be same, right?
yeah, just like in D1 and D3, the counts are same, so the values also will be same here.
Yeah, so that's my question. Like suppose there is 2 words, which is it and is, and both these words appears in same number of count in D1, D2, and D3, then it will have exact same value in both the rows.
Right. That
So,
will be
so
that will happen.
that's not a problem.
That's well. So why do you think it could be a problem?
I think now that both the words has same token, then there is no difference between it and is.
So are you trying to say the difference between the terms or the difference between the documents?
Yeah, because this not it and is represented by this value, right? Whatever we get from in this row, like currently it is 100, which is it, and is 100. There are some other columns which is not present here, but that's the number by which it is represented. So I was saying that if both become same exactly for 2 words, then both the words is having the same token, right?
No, I think many things are getting mixed up here. Let me just. So here we are saying that we want to find the representation of the documents, and the document representations are these things, the columns. We are not
Okay.
trying to look at term representation at this point. If you say representation of term,
Yeah, term,
then
like
we'll go
words.
over it.
Yeah, I was talking about term.
Representation of terms, yeah, it will be, then we need to see row wise, and it's a case that it and each, they'll have same representation. However, if you look at typical document collections, which are quite large, I mean, any small document collection also for any real purpose will have at least 100 documents. Now, it's very rare that the two words have exact same number of occurrence in each of those things, unless it is a term which is, goes really as combined thing in this.
Yeah, that's correct.
So in that case, so later on, maybe today's next part, or yeah, we'll talk about some of these term representations also, where that point will bring in.
Okay, understood, sir. Thank you.
Sir, there will be a problem with this function if CTD is 0. So because log10 is 0 is undefined. So I think wouldn't it be better if we keep if we define it as like log10 1 plus CT comma D.
Right. So even that function is explored. That's a good suggestion. People have used that also. That's a valid choice.
Okay. And in this case, if we do not choose that, but if we go by this function, then how are we going to handle the undefined case here?
It should be defined to be, so if CTD is 0, this is defined to be 0. So before,
Okay.
Okay, I
Okay.
think based on the discussion that we are having, based on the comments which are coming in, I feel that this part is kind of clear to you. And let me move on. And maybe after 10 minutes, we'll go for a short break. So, says that across the document collection, across the collection, if you see, so there are some terms which are more, which keep occurring everywhere. So they should not be very important. That's what thought that people had. And although there could be some other opinions about this, but it was well accepted that so if you look at any document, there are some words which actually give meaning to the document, and there are some words which occur accidentally, or words which give. We talk about language, right? Language as grammar, which give the desired structure to the sentences. So, for example, if we say, "I have been to Delhi last Wednesday," so have been. So this is used there to give the sentence the grammatical structure. Or say if you look at many words like is, and, are, many times these are for the structural completion of the sentences, but they do not convey any real meaning. So on the other hand, if you look at the exact keywords which are present, exact entities which are present, with that only we can get a fairly good idea about what this document is talking about. There could be some other tasks for which we need to look at everything, but at least for many tasks, these very frequently occurring words are not very important. You can also consider this to be, suppose there is a person who is to be seen in each and every party or each and every occasion, versus there is someone who, chooses the occasions or the events in a very specific way. We can say the second person is more choosy and possibly more important. I think this is a very crude example or raw example, which may not be representative of the real fact. But yeah, so that's the thing. Something which is commonplace, which occurs everywhere, typically has lesser importance. On the other hand, if something which is a little bit more rare, uh, then that is more important.
But
So,
sir, mathematically, this is still the same, right? It's again going with the noisy capture of the relative importance, even with the TFTD. I mean, like the trans frequency side as well.
so uh, for the time being, you can ignore whatever we covered till now. We're talking about a different problem. And say, for example, the word rain, uh, or say the word not versus the word say IIT. So the words not will appear in many documents. So if you have a document collection of 1,000, yeah, size 1,000, most likely all the documents will contain the word not. Now, unless it's the, so if it is a general corpus, you can expect that IIT term will be appearing lesser number of times. So the fact that this is appearing everywhere may mean that this word not giving any specific meaning in a document. It's just, on the other hand, the word IIT is present in some documents, is not present in some. That means wherever it is present, it is carrying some specific meaning or objective. So that way, if you look at the document's representation, the word IIT should have a higher say than not. So that is the philosophy that people had. Now uh, this philosophy may not hold when we are talking about domain-specific collections. Say suppose we talk about all the documents from IIT Hyderabad. We see the term IIT Hyderabad possible in all the documents. So if it is in web page, we'll see this term appearing in all the web page because most likely it is going to point to the homepage of IIT Hyderabad also. So what we say here is that terms which are rare, but not that rare that okay, it's a misspelling or something, terms which are reasonably rare, so they should have higher importance in the vector representation as compared to terms which are commonplace. Now with this, so this is the philosophy, and then then it was important to say that each word will have a weight which is a global weight. So all the vectors or the term frequencies that we have stored here, these are local to the document. So if we change the document, the term frequency will change, may change. But with each word will associate a weight, that's an importance weight of that word, and it is a global weight for that collection. Global weight in the sense, this is a so this is a corpus specific weight given to that word. So again, the choice for that we came up with is this one. So here the idea was that if a term appears in more number of documents, so suppose that count is called document frequency. The document frequency of a term T is the number of terms, sorry, number of documents in which the term occurs in the collection. And suppose this is the weight. Say if it occurs many times, its weight is less. Now, if the occurrence is less, when weight is more, like this. So, like for term frequency, we wanted an increasing function. For this weightage, we want a decreasing function. So, a function whose argument, suppose this weighting function W is a function of document frequency DFT. If the argument increase, we expect the value to be decreasing. So we need a decreasing function. And one such function that, again, a choice that people made is log 10 n by DFT. Let me explain this function. So what is N? N is the total number of documents that I have in my collection. So 1,000, 1 million, whatever. Now given a collection, this N becomes a constant. Right? And in that collection, how many documents contain D? That is in the denominator, DFT. So what do we see? If a document is appearing in more number of times, that is if DFT is increasing, so it's in the denominator. If DFT is increasing, the denominator is increasing, this overall fraction keeps decreasing. And since log is an increasing function, if its argument decreases, the overall weight decreases, overall value of decreases. That means if DFT increases, the overall thing decreases. So that's why this function is also called as inverse document frequency or IDF. So in a collection, again, let me erase all those things. In a collection, suppose there is a term T1, which appears, say, assume that we have a collection of 500 documents. And T1 is a term which appears 100 in 100 documents. T2 is a term which occurs in 500 documents. And T3 is a term which appears in 10 documents. So number of documents N is equal to 1000. So that's the assumption. Then the IDF weight for this one will be log 10 N by DFT. That means 1000 by 100. So these are all document frequencies, which is 10. And what is this value?
1.
Now for this one, what will be the value? It will be log
20.
Is 1000 by 5, right?
Oh yeah, log 2. Yeah.
Log 2, I think it comes out to be 0.3010 something.
Yeah, 0.30.
Then this one is what? Log 10 and 1000 by 10. Right? So
yeah. 2.
it's 2. So what we see here is that from T3 to T1 to T2, the count increased from 10 to 100 to 500, and the weight decreased from 2 to 1 to 3. So the terms which are more present, the weight associated with it is less. Terms which are rare, the weight is more. And you know that these frequencies may change abruptly, but there is some kind of smoothing which is happening here. So I should use the word smoothing very carefully here, because smoothing has different meanings in different contexts. So these values do not change very abruptly. Okay. So in some way, we are seeing some damping also here, very carefully and controlled kind of increase and decrease. So this is called the IDF weight. Now, if you remember, our goal was that given a document collection, for each document, how do we get a representation? So we have talked about a simple representation where we store the Boolean vector, presence or absence. In this specific case of this toy example, even if we use the raw frequency, we'll get Boolean vectors only for D1, D2, and D3, because no term occurs more than one time in a document. If there were repetitions, we could have seen some values which were neither 0 nor 1. Then we see that instead of storing these ones, we'll use the term frequency, and at the same time, since each word should not have equal importance equal importance in the collection, we need to consider IDF weight also. So finally, the value that we will store here is a product of this and this. So finally, whatever value will go inside the vector is PF T, D, and multiplied by IDF of T.
So, sir, TF, the term frequency is respective to one document, whereas IDF is across all the collection of the documents.
Exactly. So if you look at the sequence of steps which happen for a static collection where we want to store the TF-IDF vectors, is that we'll start with a collection like this. For D1, so for each document, we'll then extract the individual words. From that, we'll have the vocabulary. And while doing this vocabulary construction, we'll also maintain the count for each, the document frequency of each term. See, when we are processing D1, we have extracted all these tokens individually. We take the first word it and see whether it is there in the vocabulary. Initially, the vocabulary is empty. It is not there. So we say that it is a new word and its document frequency is 1. Then similarly for going to rain today, document frequency becomes 1. Then we take D2. Today is a word that we get and we probe here. It is there. But the count of 1 that was, this is a document D2 where I am seeing today for the first time. And the count for today in D2 is 1. Now I should increase it 2 because now today is appearing in 2 documents. Okay. It is like this. Similarly, for I, it's a new word. First time it is occurring in this one. I store I with a document frequency of 1. Now, suppose next word, not, the am, not, all these things will go like this. And suppose here we have another term called today. Today is appearing 2 times. So, today. Now we'll see today is present, and we'll also know that today appeared in this document only, so we'll not increase the count. So when we say document frequency, we say how many documents contain this term. Now in a single document, if the term occurs 1 time or 10 times or 100 times, we don't bother. Repeating this in a single document, we do not care about when we talk about the document frequency. In this way, once we have done processing all these documents, our vocabulary is there. We also have these counts, how many documents that term is present in. And once we have that, we can simply compute the IDF value using this formula. And in the same structure, we mentioned that. Next, typically what people do is, while the construction of this is being done, this vector is created with the term frequency values. Now, after we have made a pass over all the documents, the vocabulary is constructed, we then start modifying this vector to multiply each term, each of these things with the IDF of the corresponding thing, so that we don't have to open each of these documents again and start the tokenizing process. So while this is being taken, each document is being taken up one by one, vocabulary creation happens in incremental manner. This bookkeeping operation also happens on the fly, and once a document is present, this intermediate vector is prepared where we simply store the either raw frequency or the term frequency. And once everything is finished, we are done with this, we reload this thing into memory, and for each of the things, we now multiply the things with the IDFT, because this is the point where we have the final values of DF and IDF. This representation scheme is called DF-IDF representation scheme. It became very much popular. It is still very much popular. So although there are many newer kinds of representation schemes, still this one is being used and will be used for at least quite a few years, specifically when we are limited with our computation power and the documents they have certain characteristics like short documents and so on. Yeah, so this is one of the, and this modeling is also called vector space modeling, because from linear algebra course you have done, right? You know what is a vector space. So each document is nothing but a point in a vector space. And what are the axes, what are the basis of this vector space? There is one dimension for each of the words. So this is also called a vector space model. So if we change the turn frequency function, or if we change the IDF function, so we are still talking about a vector space model, but the final value that will be storing in the vector will be different.
So when you were explaining that part, when today came twice in that document, why we didn't consider because the CTD function would have changed, right? So the CTD would, yeah.
CTD would change, but here,
And yeah,
here what we are storing, these counts, these are the document frequencies. How many times the term appears in the document. So if you look at, I mean, two different things we are doing. So, so suppose we are talking about the first word, first one, it. So we saw the first it. What we did in the vocabulary, we added the term it with document frequency of 1. Then we, and for the current document, we say that for it, the value is 1. Then is exact same thing will happen. Going to rain today, exact same this thing will happen. Now we have the second it from this document. So what we will do is we'll check, is it there in the collection? Answer is yes. So we'll not make any changes. It will remain as it is. Then we say that, okay, it is appearing one more time. So for the current document, its count should be increased to 2.
the last line, sir, is the first term is the word and then the document frequency, right?
So this is the
Okay, okay.
the document frequency, the vocabulary.
So the vector space modeling will be there for all the document, for every document, or would be just one vector space model considering all D1, D2, D3 then?
So this modeling is called vector space model. In this vector space model, for each document we have one vector. You can consider as a point on this one. For D2 we'll have another vector. For D3 we'll have another vector. So this entire thing together is a vector space model.
Sir,
Okay.
Aman, you can go.
Yeah, just one last thing. So basically, each vector would be the respective CTD, the product of, sorry, the DFT and the IDFT in that case for each vector.
This is a vector where we have turn frequency multiplied by ID.
Okay. And this is specific to each document, each word, of course, yeah.
For each document, we'll have one such vector. So this is suppose this is D1, this is D2, and D3.
Yeah, each document, each word is that.
Each document one vector, and one vector has many dimensions,
Yeah,
right?
yeah, got it. Yeah, yes.
So each dimension corresponds to a word.
Got it, sir. Yeah, thank you.
Yeah, Bishop, I think you were saying something.
Sir, I have one question.
Please.
So when we calculate this document frequency, I mean, we didn't take care the future document in account. We counted till the current document. Why it was so?
So so these things were developed in. Okay, so if you look at when these NLP techniques came into existence, so one very around 1950s, when after the World War, so these veterans were actually very strong in their many different fields, and people in the US, they were not able to understand what was there in the Russian collections. So they started looking at the translation aspect. So this is one of the very first times when people started looking at natural language processing, but everything was rule-based. People were trying to understand what each word means and so on. And slowly, we started looking at different kind of automated processing and this got a major boost around 95, 98, around that time, where people started using this kind of concepts for library search. So there were collections of different documents in libraries, the traditional, I mean, I'm not talking about the packages and libraries, but the library book, articles and so on. So in that large collection, how do I find whatever I'm looking for? Now, typically in these cases, the collection were static, or the moment something was about to be launched or used, the system had seen a lot of documents. Okay? And then in 98, when Google came, they also started using this thing big time. Now there also, if you look at the case, they are indexing that entire web where there are lots of documents. Now, once you have these estimates of document frequency IDF, so it is nothing but a proxy of the weight that the term captures. Now, if you have already seen a very large collection, and from that you have gathered some statistics about the term's importance, one can have a good faith on that term, on that weight. Now, if you keep adding new documents, say suppose your original collection was very large, and you slowly start adding new documents, the counts will not change drastically. Even if they change, we have all these log things in this account, right? So the impact in the change will again be very minimal. So that's why this was a very good choice of storing the or obtaining or measuring the term importance, provided your initial document collection was significantly large and you not expect it to be updated every single second or minute.
Makes sense. Understood, sir. Thank you.
Isn't the term frequency term normalized by the total number of words, frequency for the total number of words in the particular document?
Yes, so there are many applications where what they do is they first get the vector like this, then they normalize it by dividing each entry by the L2 norm of this vector, or some other kind of application.
So one more question on it. So the TF value will lie between 0 to 1 if we normalize it, but the IDF value may lie between 0 to infinity, right?
So thing is, you store the TF IDF value in itself, then you do normalize. So that means before normalization, TF and IDF have already come together.
Can you please repeat?
See, in each cell, we store the TF multiplied by IDF value. So that
Okay.
And like that, we get that entire vector. After that only we get the normalization.
Okay.
If we do normalize.
Okay, fine.
And sir, in this scenario, then IDFT for D1 will always be 1 in that case.
No. So we multiply the TF and IDF, we get some value here. We multiply TF and IDF for this, we get some. And then we normalize this entire vector. IDF things are not changing.
Yeah, but I mean, like, what I'm saying is that in that case, the driving factor is actually TFTD only, because IDFT is because when we are considering only one document at a given time, the IDFT for that document uh, isn't. I mean, like, are we looking for example, if we are looking for it, and we know it is occurring in D1 and D2, but when we are actually making a vector for D1, that's when basically we are only looking at the TFTD portion only, because IDFT we know it is already 1 because it has already occurred in that document.
Not really. So everything has TF and IDF blended in it, right? Suppose this value now after TF IDF becomes 3, this is 2, this is 1. 3, 2, 1, and then everything else is 0. So when we normalize this thing, we'll divide by 9 plus 4, which is 13 plus 1, 14. So everything is divided by square root of 14. And here, suppose this thing only occurred 2 times. This is 0. This is 1, say. So this entire thing will be divided by square root of 5. Now, before doing this normalization, before doing this division, this term's IDF has been blended inside this. These terms IDF has already been blended inside this, and now we are doing this division by this. I mean, whatever you are saying will not happen.
When we are multiplying for example, for D1 and or maybe for D2 and it word, when you say it is 2, it will be only the TFTD factor which will be bringing that 2, right? Because IDF
No, this multiplication.
but when you're looking at the IDFT at that point in time, are you looking across all the documents then D1, D2, D3 is what I was trying to understand.
So suppose IDF of 8 is 1 by 2. 1 by 2. And this raw count was 6 here, 4 here. Now, and assume IDF of is 1 by 3. And this was 6, this was 0. And for going, it was 1 by 4. And
Got it.
4 times and 4 times.
Got it, sir. Now understood. Yeah.
Sir, just a clarification. So document frequency is nothing but a term used across the documents, like the maximum value that it can have is the number of documents, right?
Exactly. So in that case, the element will be n, and the weight will be log 1, which is 0.
So it's always between 0 and 1.
It's always between
IDFT.
It need not be between, the maximum value need not be 1.
So I think I also had the same question, but I think IDFT is actually being calculated across all the documents for that particular word, not
If you look
particular
at
to a document.
if you look at this idea, n is the number of documents.
Yeah.
In our example, n was
Okay,
1000.
or n by
Sometimes,
DFT is always greater than 1.
yeah.
Okay.
So that means this is greater than 0. That's it.
Yeah. Okay, sir.
Yeah.
Okay, it's 10:25. Let us go for a 10-minute break now. We'll come back at 10:35, and then we'll continue till 11:15 or so. Okay. So Okay, so we will be resuming our discussion. Let me check the sharing again. Okay, so I believe the slides are visible. We need a confirmation from you.
Yes, sir, it's visible.
Yes, sir. It's visible.
All right. So we talked about the basic vector space modeling. In vector space modeling, we define a vector space which is spanned by what we have in the vocabulary, the terms in the vocabulary, and then each document we represent as a point in that vector space or a vector in that vector space. Now, the length of the vector, or in other words, what is stored in each specific dimension of the vector. For that, we have many different choices. We have explored 3 or 4 different choices. One is the Boolean representation. Then we said, okay, so the Boolean value of presence or absence, you can store the raw count of how many times the term appears in the document. Then we said, okay, instead of the raw count, you can also store the term frequency, which is a function of the raw count. And the fourth scheme says, along with the term frequency, you multiply that term frequency with an IDF or inverse document frequency weight, and that product becomes the entry in that particular field. Then we also discussed that those vectors that we get from the documents now, so those vectors we can further normalize. So L2 norm is there. There are many other types of normalizations also that people have explored. So yeah, so this is what we have covered in nutshell till now as part of the vector space model. Now, after this modeling, let us try to understand, or let us try to critically analyze this representation scheme. So there are certain good things about this representation scheme. It's very, to see a vector, it's very easy to understand why the vector is like that. Right? If you see a document vector like this, where sometimes is high, sometimes is low, and all that, it's very easy to say why this has come. Now, if you work with all the full vectors in the computer vector space, then if you try to visualize that vector space and the organization of different documents in that vector space, we may also be able to extract that, okay, 2 documents are very close by in that vector space. Possibly they have the same meaning and these kinds of things. Having said that, the model also suffers from some drawbacks or limitations. So let us try to discuss some of those. So can any of you point out some drawbacks or shortcomings which exist in this specific modeling?
The sparse matrix problem. I mean, many of the items will have the values as 0, so it will be computationally very expensive.
So if the vocabulary is large, each vector also becomes large. That means we have to process very large vectors. At the same time, if you look at a document, all terms in the vocabulary, they are not present. So only a few cells in that vector, they have non-zero value and everything else is 0. Right? Now, if you're handling all these vectors, I mean, these are all sparse vectors. So the information is there in only a few specific fields, but we need to process a large number of elements. So that is definitely one concern. However, if we have sparse matrix, and the other thing is that if we need to pre-compute and store all these vectors, it requires a lot of space. Right? So one solution could be like using the sparse vector format. However, when you need to do the processing, then you need to expand to sparse vector, or so the problem remains. There could be some workarounds, but the core problem remains. Good point. Anybody else?
High dimensionality.
Doesn't include the the order of the word sequence into account.
Does that is true? The sequence is not taken into account, and without the sequence, sometimes the meaning that we get may become distorted, or we may not get a context or complete meaning of the document. Now, people realize that, and one remedy that they offered is that, okay, we understand that in this model, the complete sequence information cannot be used. So if you have these two documents, A is better than B, and B is better than A, you can very easily see that these two vectors are going to get the same representation. However, the meanings are completely opposite. So what they said is that, so instead of having in the vocabulary all terms which are present in the document, we can also use pairs of consecutive terms. So for example, say we said it is a term which will be there in the vocabulary. Is a term which will again go into the vocabulary. Watch is a term which will go into the vocabulary. Similarly, it is going to rain, rain today. So this kind of consecutive pairs of terms will also be there in the vocabulary. Okay. So these single terms are called unigrams. Uni means one, and these are called unigrams or word unigrams. On the other hand, if you look at rain today, so this becomes a bigram. Okay. So my vocabulary will be a combination of unigrams and bigrams. If needed, we can also have 3 consecutive words, which becomes a trigram. So although we are not able to store the complete sequence information, some bit of sequence information we can store. Okay, now in the vocabulary, we're going to use unigram, bigram, trigram. Now, do you see any issue that comes due to this choice?
Yes, first thing is there will be so many, the vocabulary size will increase.
Right. The vocabulary size will increase. And that's a major consideration because we are saying with unigrams only the vector is large. Now, if you want to use bigram, it will be even larger, even sparser, and so on.
And
So
even with the increased vocabulary, we are only able to capture context consists of only 2 words, right?
True, true. So we say that we're not through this, we're not providing a complete solution, but it's some kind of workaround, some kind of a small thing we're providing. I agreed it will not be a complete solution. And what you have said is right, that for that also we are expanding the vocabulary very largely. So what they said that, okay, then in that case, let us try to see how we can constrain our vocabulary. Now, it's not written in stone anywhere that every single term, every single unigram, every single bigram, every single trigram should be present in the vocabulary. So we can be selective in deciding what all terms go into the vocabulary. And that was a major decision, and that was a major thing which also helped people to restrict the vocabulary size. So we said that I'll not store all bigrams. Suppose for all bigrams which are there in the collection, for each of them we store the count. Okay, how frequently they are appearing. Now, when I say count, we can see, okay, how many different documents they're coming from and things like that. And now we can have an upper cutoff and lower cutoff. So if the bigram is occurring in very small number of documents, maybe we have a collection of 10,000 documents is occurring in only 5, we'll not use it in the vocal because it may not be important. On the other hand, if it is there in more than 90% of the documents, then we see again it becomes a very commonplace thing. Then also we drop it. So we can decide an upper cutoff and lower cutoff. Typically, those are collection specific, and that way bigrams can be added. Similar thing could be there for trigrams, even when people have used it for unigrams also. So that is one way of restricting the vocabulary size. And people also say that there could be certain things which could be important. Say, for example, suppose there is a name of a person or a name of a place. So these things we'll try to use. So when we say bigram, trigram, other things, we add some specific types of word phrases that will continue to store in the vocabulary. Some of these things could be the names of specific things like persons, location, event, and so on. So this was one way in which the vocabulary can be controlled. We decide what should go in the vocabulary and what should not be going. And due to this, also people observe this becomes a very useful consideration. The performance and overall performance versus this vocabulary size trade-off can be addressed to some extent here. Okay, so we have talked about two different factors. One is that large vectors in vector space model, and the second is absence of the sequence information. All right. Do you see any other drawback?
I think semantics is also not being taken into account.
Elaborate.
For example, if there is another word synonymous to a particular word, then they will form two different words here.
Right. So if two words they mean the same thing, but they are different words, then there will be two different dimensions in the vector. Okay, two different fields in the vector, two different axes in the vector. So although they mean the same thing, their overlap is 0. So that way, yeah, the model is not able to understand that these two documents may have some connection or similarity based on the synonymous terms. So anyone else with any other observation?
And sir, we are only considering the verbiage here. We are not considering the exclamation commas and the other. The
Okay, so the punctuations
punctuation.
we are ignoring. Okay, and you're saying that punctuations may also cover.
They might change the context, like we were talking about the unigrams, bigrams, and the trigrams. They might also be useful in setting the context.
Yeah, so this is one more of them, although that can be handled. Okay, anyone else with any other last observation?
Sir, here every document we consider as a dimension. So if you have so many document, there will be a lot of dimension, right?
So here we're talking about document representation. So every term is a dimension. So for each document representation, each term is a dimension.
Yeah, suppose there are like millions of documents. So like D1, D2, D3 will go till millions, right?
So every document will have its own vector. So if we have 1 million documents, we'll have 1 million vectors, one for each document.
Oh, so document is not dimension. The word term is dimension.
Yes, we're talking about documents representation. So documents representation.
But the dimension of the term will increase as the number of document increases, right?
At this point, we are not concerned about the dimensions of the term. So we are processing the documents. We are not talking about the terms, representations, and so on. So we are only, in this diagram, we are only concerned about the column.
Okay.
Okay, so the points that you all have mentioned, those are actually captured in the next one. So words are considered as their lexical appearance, which means that synonymy is not considered. Then topical words are not used. Say light, bulb, auto, car. They are related But then in this representation, again, they become different axes. And if there are two different axes, there are vector space where axes have there is a linear independence, right? So projection of this axis on this one and this axis on this one. So these are zero, no overlap. That means there is no sharing of any meaning there. Then another thing is that polysemy, the same word meaning different things. So here, irrespective of the meaning that the word has, it will be one dimension of the vector space only. So everything is collapsed here. So that is also a problem. This is something connected with the context part, and then long vectors. Okay. So these kinds of things should be addressed. In some cases, we could do some additional thing to take care of some of these concerns, not in the full way, but yeah, I mean, a few such options where storing the bigrams, storing the trigrams, and also having some cutoffs to control the vocabulary size and so on. But as it has also been observed by all of you, that there's some simple workaround doesn't solve the complete problem. So there is a need to look at some better techniques. Now, this DFID based metrics, it worked well in many different cases when we try to understand the things in an overall level, or even for very specific tasks like classification, clustering, identifying similarity, and so on. It worked well, but people, what they saw is that still the performance is hitting a ceiling. So there is, even after how many different functions modifications you do, how many engineering tricks you apply, there is a point beyond which it's becoming very difficult to increase the accuracy. So the ceiling has to be broken, and that meant possibly whatever drawbacks we are seeing here, we need to address them in a much more better way. And this thing was going on since long, and then from 2012-13 onwards, we started seeing many different which changed the way these representations are used. Although having said that, they are still very powerful representations, and for many applications, only this much is sufficient, and we do not need to have other kind of representations, or we may not benefit a lot by using other kind of representations, which will require the computation cost and other things significantly. So with this, let me go on to the next slide deck. Yeah. Okay. So the two major things from the list of problems that we had, two major things are that we need compact representations. Okay? For all the different words, among them, we need to find the relations and somewhere so that it leads to better representation scheme. So with that, the next shift in attention becoming, okay, let us try to learn the representations of the words. Okay, so here our focus was mainly on representing the documents, but a document is composed of many different words, right? So if somehow we get a better representations of words, somehow they can be fused, they can be combined to get the final document representation. So that was the thought. So the idea is that we'll represent each word as a low dimensional vector. Okay, so we'll represent each word using a low dimensional vector. Word similarity will be related with the vector similarity. So for each word we are having a vector, and if two words are very similar, their vectors will be similar. If two words are very different, their vectors will be different. So here, the key idea was that we can observe the surrounding words of every word, and typically, words which mean similar are surrounded by similar words in many documents. So that was the idea. That was the observation that people had, and based on that, they design certain techniques. So the question is, earlier when we look at the document vectors in TF-IDF, it was very easy to see, given a collection, how to get the vectors. But here, how do we get the vectors? So that all these are maintained. Right? So the idea here is that we learn the vectors. Okay, we learn the vectors. So we have a document collection, and we do not say that this is how each vector will come. Step by step, you do this. You count this, you put this, you apply this transformation. Not like that. So based on the document collection, we will learn the vector representation using some kind of machine learning algorithm. Okay. Now these vectors are also called embeddings because we're embedding the words in a large vector space. So the mechanism of learning these vector representations or embeddings is called word embedding, and it is a specific kind of representation learning because we are learning the representations of the words in the vector space. So this diagram shows intuitively what we are trying to have. So suppose in the 2 dimensions we have plotted the vectors of different words, and what we see is that cheetah, jaguar, tiger, leopard, all these things are coming close by. Then flora, flower, orchid, foliage, these are together. Pelican, seabird, bird, raptor, these are similar location. Somehow, word similarity is also related with vector similarity. To words, if they're similar, words which are similar, their vectors are also similar. That's why they're lying in this closed region of the vector space. So the question is, idea-wise, all these are fine, but how do we learn this? So here also, I'll start from some of the statistical techniques, and then we'll go on to modern, learning-based methods. So the first one was first one was using the statistical cues, where we make use of a very solid mathematically supported technique called singular value decomposition. So I believe it might have been covered in your linear algebra course also. So that if you have a matrix, okay, that matrix is A, and this matrix A you can decompose or you can factorize as a product of 3 different matrices: U, sigma, and V transpose. Okay, these 3 matrices, if you multiply like this, you multiply by sigma multiplied by V transpose, you get back A. Now this A, was it covered in your linear algebra course or some other course earlier as part of this MDS program?
Yes, sir. It was
Yes,
the
sir.
basics was covered. Yes.
Okay,
For
now
23 batch, it wasn't.
Yeah, for 23 it was not covered.
okay, so people who are aware of singular value decomposition, either from MDS or from your earlier study in your bachelor's program or even before. So do we need A to be a rectangular vector or a square vector? Sorry, rectangular matrix or square matrix or what?
Yeah, we can SVD applies to the rectangular matrix as well, unlike the normal PCA.
So SVD, singular value decomposition, you can have any kind of, it can be square or it can be rectangular. Now, we see that there are 3 things like U, then there is sigma, and then there is V transpose. So, right, we already have a diagram here. So A equal to U sigma V transpose. Now suppose A is a matrix of dimensions m cross n. can you tell what will be the dimensions for U, sigma, and B transpose? What will be the dimension of U?
We can
The diagram
say
gives the hint.
M cross
U is
A.
n by n.
U is
N by n. M.
U is M by M. And this one?
M by N.
And
M
this n
cross
n by
N.
n.
Right. And now if you do this multiplication, you see that, okay, these multiplications are compatible, right? And then the final thing is M cross N, which is the dimension of A. Okay, so dimension, we are clear. Now what will be the entries in U? So we are only given as A, and we are saying that for each A will be having a decomposition like this. Then from A, how do we get the representations of U, sigma, and V transpose? So the columns of U are orthogonal eigenvectors of A transpose. So you have A, then you can very easily compute A transpose. And if you have two matrices A and A transpose, very easy to compute their product. And then there are libraries which can give you the eigenvectors for to predict a matrix. Okay. Now the columns of U are the orthogonal eigenvectors of A transpose. So this one is an eigenvector for A transpose. This one is an eigenvector of A transpose. This one is an eigenvector of A transpose. And you can say that orthogonal. Actually, you can also call it orthonormal. Can anyone tell what is the meaning of these orthonormal vectors here?
Unit orthogonal.
Vectors which are of unit dimension are perpendicular to each other.
Right. So here we have m columns. So each of these m columns, that is each of these m vectors, are perpendicular to each other. Okay, that's one thing. And secondly, each of these vectors is a unit vector. So a very nice structure is there in U, and the columns of V are orthogonal eigenvectors of A transpose A. Very similarly, you compute A transpose A, and from that you can get the orthogonal eigenvectors from here, and then you will get V. And remember, this is columns of V, and here we have V transpose. That means we are talking about the rows of V transpose. They will also be orthogonal to each other, that is perpendicular to each other, and each of these will be one of these will be a normal vector. Okay. Now M cross N. What is M cross N? Sigma. The sigma which is of dimension M cross N. What is that? Now A transpose has eigenvalues lambda 1 to lambda r. Okay. R stands for the rank. So they are the eigen. Now what can be shown is the eigenvalues lambda 1 to lambda of A transpose are same as the eigenvalues of A transpose. Okay. So you can take A transpose, find the eigenvalues of that, or take A transpose A, find the eigenvalues of that. And those are this thing. And for each eigenvalue that you get, you take the square root. Okay. And these are called the singular values. These singular values you put in the diagonals of sigma. Okay. So that's why you see some diagonal entries here. So it has m cross n dimension, m rows and n columns. Okay. And here in this example, if you look at the figure, m is larger than n, right? More rows and columns. So between m and n is smaller, so we can have only n diagonals. So if m is 5, n is 3, we can have 1, 1, we can have 2, 2, we can have 3, 3, but we can have 4, 4. We cannot have 4, 4. So we have only 3. So number of diagonal entries that we can fill in is the minimum of m comma n. And what are those diagonal values? Just positive square roots of the eigenvalues. Okay. Now, we said that A can be square or rectangular. If it is square, fine, everything will be m cross n here. Now, this is the rectangular case where more number of rows than columns. On this one, it has more number of columns than rows, right? M less than n. Now, here, again, this will be m cross m. This is m cross n. This is n cross n. But the thing is, here we'll have m number of entries. But if you just collapse all those things as this kind of formulation, A equal to U sigma V transpose, we can write it in that manner in all the cases where more rows than columns, more columns than rows, and so on. So yeah. Now, okay. Question is, we talked about we were talking about NLP, we are talking about documents, terms, and so on. Suddenly, we are talking about some linear algebra concept. So how are these two connected? So if you look at you remember the diagram, right? Where we had the terms in the rows and the columns in the documents in the columns.
Yeah.
That matrix can be our A. So we are given a collection from that using something. So it can be using term frequency or TF IDF or whatever, normalized, non-normalized, whatever. So if we are given a collection, we can get a matrix representation out of that. So the matrix representation can be term document matrix. So term document matrix means the rows will be terms and the columns will be documents. So this we can have, or we can also have document term matrix. So essentially, we are having a matrix initially. So we can apply singular value decomposition on that. So right now, before we go there, we were talking about eigenvalues, but eigenvalues are defined for square matrices, right?
Yeah.
But here we are talking about rectangular matrix. So I mean, starting with rectangular matrix, but we are talking about eigenvalues. How do you connect these two?
For the A transpose, so basically that multiplication with the transpose will give us the square matrix, right?
Absolutely. So we are not talking about eigenvalues or eigenvectors of A. We are talking about eigenvalues, eigenvectors of A transpose and A transpose, right? Now, A transpose is a square matrix. So if A is of dimension m cross n, A transpose has having dimension n cross m. We multiplied them together, we got an m cross n matrix. Similarly, A transpose A is n cross m. A is m cross n. We multiply, we get m cross n matrix. So these are square matrices, and they are positive and definite also. They are the way this multiplication are happening. It's something like A square we can assume. So and this one. So they're positive semi-definite. So eigenvalues and eigenvectors will be there for that. So it is very much valid computation that we are doing. Now let us come back to the term document thing. We are starting with a matrix like this, and we are doing this decomposition. So now what is the interpretation of that? We can say, okay, we're taking matrix, another matrix, another matrix, but when we are talking about a real scenario where this thing is being used, I mean, how do you connect the real concept with this matrix? So what is the significance of the rows, columns, and other things in the context of the underlying problem, which is term document and so on? So if it is a term document matrix where each row is a term, now you can add, and there are m terms, right? And here also we have m rows. And say that row 1 is a modified representation of term 1. Row 2 is a modified representation of term 2. Row m is a modified representation of term m. Okay. Similarly, there are d number of documents. So each of these is now a representation of a document. Each of these things is a representation of a document. Okay. And you can say that Okay, the same thing will hold if we talk about this. Now, and these vectors, you can, sorry, these singular values, you can consider as some kind of weighting factor. So there, this is the representation of the term or the term vector. Here with the representation of the document or the document vector, and they are getting multiplied. And in that multiplication also involved are some singular values. So for each of these dimensions, there is some importance associated with these dimensions, which are captured by singular values. Some number will be large, some number will be small. So if this one is very large, then that means this component and this component, I mean, this component is actually very significant. And how much is the belongingness of the term in that component, and how much is the belongingness of this term in this component. So these things will be multiplied with this. So if it's an important term, and this dimension is important, which means this dimension is important, then yeah, the entire, so this multiplication will have a higher weightage. So before I go there, one thing that I should here typically in this sigma, these singular values are stored in decreasing order, which means this one is greater than this one, which is greater than this one. And this is done for a reason, that is, if you have this one, right? So suppose you reorder them, singular, well, sigma 1, sigma 2, sigma 3, you can permute them in 6 different ways. No, here it will be three different ways. And suppose you interchange these two. So what you can intuitively verify that if we interchange these two, you can do some reordering of the entries in U and entries in V, so that you get new U, new V, and sigma has also changed because these two are interchanged, but the product remains the same. Right? So you interchange these two, you get a new sigma. Again, you can permute the entries in U and V accordingly, so that this multiplication is still valid and you get back the A. So which means this singular value decomposition will have multiple different solutions. Now, in one way to fix and say that okay, we have a unique solution is that you put some restriction on the eigenvalues which are left. So that's why we say that even all these libraries for a singular value decomposition that you may use, you can verify, will return the entries in sigma in decreasing manner. So once it is there, U and V becomes fixed, and we say that we can say that okay, for term 1, this is the representation. From term 2, this is the representation, and so on. Even for documents also, we can say this is the representation for document 1, this is the representation for document 2. So maybe I'll just rush through and try to conclude first. So one thing again to be noticed is that, this is a diagonal matrix. That means all the off diagonal entries are 0. Now, this shaded part here is multiplied with this shaded part, which means, all these are, since all these are zeros, multiplication with these things have no effect at all. So all these things are getting multiplied by zeros. Similarly, if we talk about, this part where all these entries are zeros, these are getting multiplied with this part. So that means whatever entries are here in this region, they have no significance in the context of this computation because they're getting multiplied by 0. Now that gives people the idea, okay, then what if I make this also forcibly 0? Now, if this is made 0 forcibly, that means we have another band here, which is 0. That means this column also will become insignificant, and as this column has now become all zeros, this row also will become insignificant. What if I make another 1 0? That means we have one more band of 0 rows, which will get multiplied, which was getting multiplied with this, or which is getting multiplied with this. So this thing also has no effect. On the other hand, we get one more column, which is now all zeros. That means this is also has no effect. That means we can drop this from our scheme of calculations. Now let us try to generalize this. So we had our A, that we try to decompose using singular value decomposition as U sigma B transpose. Now, suppose we have the m number of, suppose we had some n number of singular values here. Suppose we said we'll be retaining only k. We'll returning only k singular values here. That means n minus k entries will set to 0 forcibly. That means equivalent number of columns disappear from here. I mean, functionally disappear from here, and equivalent number of rows functionally disappear from here. So the number of effective columns here become it was m cross n, right? N minus k, and number of effective rows here become n minus k. Now, in real setup, if you consider that you had, say, 10,000 documents and 1,000 terms or whatever, 1,000 terms and 10,000 documents, just writing 10, 0, 0, 0. So this is 1,000 cross 10,000, and here you will have 1,000 number of diagonal entries. Sorry, here you will have 1,000 number of diagonal entries. Suppose I say I'll get only 10 of them. The remaining 990 I'll be setting forcibly to zeros. That means the effective number of entries in each row will now become only 10. The rest 990 from this point will be zeros. Only effective entries here in this vector also will be 10. Everything else is zeros. So this, and then what people showed means it is showed in proper mathematical way that since you are modifying the vectors U sigma and B transpose, if you after all these modifications, the new U, new sigma, new B transpose, if you multiply, definitely you are not going to get back the original. There will be some deviation, there will be some difference. So, but if you compute the magnitude of that difference, so A is a matrix, the original matrix, and then this AK is what you get after retaining only k singular values, and yeah. Now these two matrices will be of same dimension because the dimension of the original vector is not changed, but many things we are making zeros. Now this difference you can compute. So this is called Frobenius norm. Two matrices of same dimension, you can very easily take their differences, and then you are there with a resultant matrix. Now for each cell, you look at the matrix, look at the entry, raise it to square, sum all these things, and then take a square root. Very similar to how we do L2 norm for a single vector. This is something like L2 norm for a matrix. So each term you take, you raise it to square, you add them together, take the square root. Now, this is actually a rank K matrix. So what it shows, so among all different rank K matrices of dimension m cross n, the one which is closest to A can be obtained by following this. Which means we can follow a step-by-step procedure of setting some entries in sigma to 0, and in the process, whatever approximate AK we get is very close to the original matrix A. Now these people then, I mean, this was a very exciting result. Why? Which means whatever information is contained in A, kind of the same information also captured in AK. And earlier we were talking about term dimensions which are M, or document dimensions which are N. But now the effective dimensions for terms will be K, and effective dimensions of documents also will be K. So instead of operating with 1,000-dimensional vectors, we can operate with only 10-dimensional vectors. If needed, only 5-dimensional vectors. So terms can be represented using the entries in UK, where A is the term document matrix. If A is a document term matrix, then documents will be represented using entries in UK. Why? Because number of rows here is same as number of rows here. Okay? So if the rows are terms, here we are talking, you represent terms. If the rows are documents, rows represent documents. And documents can be represented using the entries in VK, and we can work with dimensions, which is much less than 10. So any questions here?
So the number of k, if just like we would be basically for each value of k, will compute the ak and then we'll find the magnitude in that case. Or
So we decide.
Yeah.
We'll decide what is our k. That can
So,
be. Yeah.
So this k value is decided based on the eigen values, like whatever we decide in the sigma matrix. I mean, based on the cutoff, to capture the maximum dependencies, or how it is decided, how we decide the k values.
One way could be like, so you see, so you add up all the eigenvalues. Okay, your eigenvalues are lambda 1 to lambda, right? You add up all of lambda 1 to, and now you go from lambda 1 to lambda 2 to lambda 3 and see how much proportion of the total of the sum you are recovering. So once you see, suppose the summation of all the lambdas is, say lambda 1, lambda 2 till lambda r is lambda. Okay. Now once you look at once you consider lambda 1, you are covering lambda 1 by lambda, that proportion of the total eigenvalues.
Yeah.
Suppose we say, okay, let me consider lambda 2 also. So we are covering lambda 1 plus lambda 2 out of total lambda. If you consider lambda 3, suppose you add them up, lambda 1 plus lambda 2 plus lambda 3, and you are covering that one by lambda, this much fraction. So one can set a cutoff and say that, okay, whatever is the summation of all the eigenvalues, I'll try to retain the 90% of that sum. And whenever I go, beyond that 90%, so this is one way in which one can be, this can be done. I mean, you need to decide that threshold for sure. 90-95% are a good choice, and in fact, for all these real kind of examples, they are scenarios that the large eigenvalues are actually very large, and very soon you'll be able to cover 80%, 90%. And the other thing is that based on your compute, you can decide, okay, I have these many documents, these many terms. If I need to do these many operations, okay, maybe 100 dimensions is good or 50 dimensions is good. You can just stick to that.
Okay. Yeah.
Okay. So, so this is, I believe this process is understood. You have a collection. From that, you can have this term document incidence matrix. You take this, you feed it to this SVD, and you tell how many to retain, how many singular values to retain. And based on that, you can get the that many dimension representation for the terms and the documents. Now, this process is called truncated SVD because the original SVD, from the original SVD, you are setting something to add some other singular values to 0, and essentially this UV, some part of it is getting truncated in some sense. The left out part is having no importance in the calculations. So this truncated SVD is a very good choice for representing documents and terms. And with some experience, so there was a data set which was given BBC news collection. So what we did is we took all the terms. Now here we are talking about term representation and document representation both together. Earlier when we talked about vector space model, we didn't talk about term representation. Here, suppose all the terms, we now have their representations here, right? And these terms, then we clustered using very simple k-means clustering, no fancy thing. We said, okay, we'll be going ahead with 10 clusters, and now let us compute. Let us see which term goes to which cluster. And k-means will give non-overlapping clusters. So what we saw, now this is a very old data set, and this experiment was also done some time back. Cluster 0, you see that some terms which are very related, they are coming together: mobile phone, broadband, digital. Then cluster 1 has show a series, star, and so on. Then cluster 7, film, Oscar, awards, actor, and so on. So we see some very nice kind of semantic grouping of terms. So this shows, although the it was very mathematical, very statistical singular value decomposition. It comes from that theory. It can be very nicely used for this domain. So this is one. And then what you can do is you can take one cluster, and whatever there is one cluster, there is another cluster, there is another cluster, and so on. You can take one cluster and you can do further subclustering here. And even those things, those level 2 clusters were actually very meaningful, which means it actually worked well. And there was one more example that was given by people in Microsoft when this thing, when they proposed this. They looked at they looked at 9 different documents. 5 of them come from similar categories, which is mostly human-computer interaction, and 4 of them come from some other category, which is related to graph theory. And now if these are the documents, from this they can create a term document matrix. Okay, here we have terms, here we have documents. So 5 plus 4, 9 documents are here, and these are the terms, and they consider all those terms which are appearing at least twice. Okay, and those are here in italics. Human interface, machine possibly occurs only one time, so it was dropped, so it's not in italics. So these is the vocabulary, these are the documents, and these are the represented. They use the raw frequency based representation. So 0 means absent, otherwise the count of occurrence is there. Now then they did SVD on that, and after obtaining the SVD, they did a truncated SVD by retaining k equal to 2. So now each term is a 2-dimensional vector, each document is a 2-dimensional vector. And when we have this 2-dimensional vector, it is very easy to project and plot on a paper on a 2D surface and see. And that's what they did. So if you see here, graph, tree, minor is a graph terminology. They are in some region of the space, right? Then we have interface, human. These are also close by. On the other hand, C1, C3, C4, all these C documents are in this region, and M documents are being pushed here in this region. Right? So yeah, M2, M4, M3 are going in that region. And here M3, 10, 11, 12 means M3 contains term 10, 11, and 12. M4 contains term 9, 11, and 12, and so on. So what we say is that the documents are getting grouped together nicely, the terms are getting grouped together nicely. So in some sense, this way is capturing the semantic dimensions very well. And okay. So with this, I think so. So with this, I think we can conclude here. If there are any questions, we'll take that up. Otherwise, we'll conclude today's class here.
So just
why?
one. Sorry.
Okay. Yeah, can go ahead.
Just one thing. So the key that we are trying to find is actually clustering the words together. With the increase in k, we are increasing the clusters in a way.
So it says number of dimensions, and what we saw is that from U and V, they're orthogonal to each other, right? So in some sense, that may say, okay, these are the number of dimensions in the new vector space that we are trying to find out.
Yeah, because initially when we did SVD, the dimensions, they remain same for sigma. But we tried to increase the value of k, like reducing the dimensions. So as we kept on reducing the dimensions, is it like clustering with the new formed vectors?
Well,
because the later example that you showed, it seemed like as the k increased, the words were going together in a clusters. Is that something we can relate?
K is the K will be the number of semantic dimensions that exist in the collection. And in this example, what we see is that certain things are coming here, certain things are coming here. So essentially, from this example also we saw that the way the example was created, there were documents from 2 different types. So in that sense, 2 also makes sense. So, but it may be the case that when we're talking about 10 dimensions, we see that along one dimension, so this is one dimension, this is another dimension. So we can see some things here, we can see some things here, and we may also be able to see something which is here. We may also be able to see some groupings here. So it depends on whether the number k that we specify is really representative of the number of different topics which are there, or which is more, which is less. That may have an impact, but it's a step towards that direction. Now if you know the exact number of themes which are there in the document, then we can say, okay, each dimension may talk about one cluster and so on. Otherwise, we can say that there is one cluster which is in the convex combination of the dimensions.
And
How can we prove that they are indeed forming clusters, or any intuitive understanding of it, how it is happening?
Uh,
Mine is also same question, sir. Like here, no learning is involved, and it is just like SVD. So why it is forming the cluster? There is no intuition of meaning anywhere in the word.
so it's something SVT, if you look at it, very similar to what we do in principal component analysis. So there also, if you look at the dimensions which come, so dimension of the maximum spread that comes out, right? So that can be proved. You know, the maximum spread uh, in one direction. So spread for a single point you can compute, and then for all points, what is the spread that together you can compute, and then you can try to maximize. So this optimization is handled inside this. So that way, so in PCA, what happens is that the dimension of the maximum spread, that's your first uh, eigenvector, principal eigenvector. Then the one which is orthogonal to it is the second most important, like that. It is also something of very similar sort. So here we are doing AA transpose, right? So it's something similar to the covariance matrix that we try to find out in PCA. So from optimization principle, it is trying to see what is the dimension along which the maximum information is spread. Now, yeah, so this analysis, what we do here, is also called latent semantic analysis, or LSI, sorry, LSA. So latent semantic analysis. So what it says is that whatever meanings which are captured in the collection, that we will try to find out. This now, that meaning is concerned with this S, and the meaning was actually hidden in the collection, but we are trying to make it surface up. Now hidden meaning is latent, and this analysis. So we are not doing it explicitly, but the way when you're doing, so it's all related with rank. We talked about rank, right? A minus A K, where rank K matrix, among all possible rank K matrices, which one is most important here? And what is rank in a matrix? The number of, most informative, number of informative dimensions. So in that way, things are connected. So if you can express your entire matrix using k different dimensions and all other rows or all other columns equivalent, you can say, okay, this is a linear combination of others. That makes, I mean, that helps you identify what is k. So here also is like, there are many dimensions which group together. There are many representations which group together, many terms which group together to give meaning to a new term. So that is capturing the term relatedness. So when in matrix terminology, we say that, okay, one row is a linear combination of other rows. Here we say that one term is a linear combination of other terms. So if we say that, then whatever is conveyed in this is possibly conveyed by using some pieces of information from some other term. So, and then we're trying to get the best k axis from this matrix. So that way we can say, okay, best k semantic dimensions we are trying to get. So in that way, some analogy can be built, although we are not making any explicit optimization with respect to the meanings here. Okay, not sure whether it was very convincing or not, but intuitively that connection can be made.
But maybe when we are trying to draw the similar semantics out of that, in that case, let's say there are like 10 different terms used to represent the same emotion or the same meaning in a way. But let's say each term, like 20 terms are there, and each term is used, let's say 10 times. So basically, had there been only one word, there would have been 200 representations of that word. But now they have been distributed for like 20 terms and in the 10 different instances. So isn't it gonna be reducing the effect of that term or verbiage overall in the representation?
I'm not sure whether you got the complete meaning of what you tried to say.
So basically, let's say there is a one word or one emotion which is being drawn out of all the documents, but the problem is that each word was represented. So there are like 20 words were used, which were trying to convey the same notion in a way. So because there are like 20 different representations, how the semantics is being drawn in a way with the bringing it to the surface in the other slide that you were showing, because every document is talking about some different verbiage to represent the same notion.
So there can be each notion or theme or topic. So
Yeah.
in say concept, that is a semantic dimension, or can also call it a topic in some sense. So we talk about the same topics. We used a very typically the topic will be covered by a set of words which are connected somehow with each other together. The moment the topic changes drastically, we start using a different set of words and so on. Now this one will try to get all these topics as dimensions, and the words which are very close to those topics, they will be uh, defining that dimension. So you can say that, okay, suppose there is one topic, one dimension which is for say graph theory. So all words which are actually in that will lie very close to it. Their projections on that dimension will actually be very high. On the other hand, if there is another topic which is very different or in some sense orthogonal, then all words which are representative of that semantic dimension, they'll have a very high overlap in that. That means they'll lie very close towards that axis. So this is one way of viewing it.
Okay. Okay.
So here the semantic behavior is dependent on the occurrence of words, right? We are not inherently deriving semantics between the words, right?
So we are not explicitly deriving, it is being uncovered by the method itself.
So this can be considered as a limitation of SVD, right? Yeah. Because it is dependent on the occurrence of the terms and how.
So it's a data-driven thing. So so that way all data-driven approaches will have that, unless we have a way to add the human knowledge or augment with some kind of guidance. So here the starting point is the collection that you provide. From that it will try to get it. So it's completely data-driven, and there is, yeah, we do not pass it, we do not feed any other information to it.
Okay, got it. Thank you.
And sir, this clustering, what you shown on this SVD, was it created from a unigram or it was from diagram or n-gram data?
It was from unigrams only. So that's why you also see unigrams here.
Sir, if you don't mind, can you explain again, how did we come to the clusters from SVD? Like we just did splitting, right? Which particular matrix are we focusing on to do the clusters?
So if you look at this, so this is the original matrix, where term document matrix, and after doing truncated SVD, we take the k-dimensional representation for each term, and these terms we are trying to cluster. So each term is now a k-dimensional vector, and yeah, and then we use k-means clustering based on these vectors simply.
The key you're referring to here is the rows that we are emitting from sigma, or the columns.
So each term is now a fixed dimensional vector, and these vectors we input to k-means clustering and set k equal to 10. So identify 10 clusters from it, and these are the 10 clusters. So this, we were saying k here as well as here, so that was the confusion. So suppose we say these are all d-dimensional vectors, okay, d-dimensional vectors. So each point, each term is now a d-dimensional vector. All these n number of d-dimensional vectors we fed it to k-means algorithm and set number of clusters equal to 10, and these are the clusterings that we get.
These are term vectors, right? Modified term vectors.
Term vectors, yeah.
Okay, got it. So the k is not dependent on what we were doing earlier, omitting the columns, or
It's not related, but
okay.
if we know these many topics are there and we set exactly that k in SVD and exactly that k in clustering, then we may see. In fact, there are some cases where people say that some interesting dimensions also come up, which is present in the data, but we didn't imagine. So that's that. Okay, so let us stop here for today, and then we'll meet again based on our class schedule. Okay.
So can you please share the material that you were using today, the slides? That would help us.
Yeah. Okay. Thank you. Bye, everyone.
Continuing in the same topic in the next class? Or
we'll talk about presentations. We'll continue on with presentations.
Okay, so next class will be taken by you. Next NLP class.
We will see. We'll see. I am yet to look at the schedule. Yeah. All right, everyone. Bye.
Thank you, sir. Thank you.
Thank you, sir.
Thank you.
Thank you.